Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book. And I'm wrapping up chapter 6, which is on group theory. I just have one more lesson to go after this one. But, last time I talked about wallpaper groups. Those are kind of two-dimensional groups. They're just the groups corresponding to every possible type of wallpaper pattern. Turns out there's 17 of those. But the three-dimensional analog of those types of groups are what are known as crystallographic groups. And it turns out there's a total of 230 crystallographic groups. I'm not going to talk about all of them because there's way too many. I thought guys might be interested just to see a diagram. This is actually a poster somebody came up with showing all 230 crystallographic groups. And what's interesting about this to me is that there are known crystals with each of these 230 different types of crystallographic groups. And another thing I think is kind of interesting is that I think 11 of these 230 come in two varieties that are kind of mirror images of each other. There's a left-handed variety and a right-handed variety. They would look the same except that one's a mere reflection of the other one. And I guess that can actually give rise to different chemical properties. There are what are called chiral molecules. I'm not going to go into that in this list, but this is kind of interesting. You see this a lot in organic chemistry. But anyway, so I just thought I'd show you that. Another thing I think I should say about these crystallographic groups, just like in two dimensions, that they correspond to lattices. And I think there's only 5 different kinds of two-dimensional lattices. What are they? There's the kind of the generic kind. I don't even know what that's called. Where there's no special relationships between the two generators. You just kind of get an arbitrary parallelogram for your fundamental region. But then you have some with more symmetry. You have rectangular and rhombic, and the ones with the most symmetry are square and hexagonal. So that's 5 different types of lattices in 2 dimensions. But then in 3 dimensions, you actually get 14. And here they are. And they actually come in 2 different varieties of 7. I don't remember the names offhand of all these. There's like monoclinic, triclinic. You can read them. Simple cubic, face-centered cubic, body-centered cubic. I guess there are 3 different kinds of cubic. And then simple tetragonal, body-centered tetragonal, hexagonal, simple orthorhombic, body-centered orthorhombic, body-centered base-centered orthorhombic, face-centered orthorhombic, rhombohedral, simple monoclinic, base-centered monoclinic, and triclinic. And that's what they all look like. And I even remember a few particular crystals. Like I think salt is simple cubic, and I believe diamond is I forget which one diamond is. It might be face-centered cubic or something. But anyway, you can look these up. I think benzene is like hexagonal, but and I just saw this today. I think this is kind of interesting. So, like I said, there's really only 7 different types of, I guess, what you would call not the fundamental regions, but the kind of I guess they are the fundamental regions. But then you have different subcategories within each of those. So remember, cubic. There was simple cubic, face-centered cubic, base-centered cubic. I'm not going to go through them all again, but I think this is kind of a neat diagram. Shows them as a heptagon. And I think this one's kind of neat too. If you don't pay attention to what's inside these fundamental regions, you just get these 7 different kinds, and then on the bottom they show you particular crystals that have these different types of crystalline structures. So I think this is kind of neat. Anyway, yeah, crystallography is pretty interesting, I think, and it's all based on this same idea. Kind of like the wallpaper groups, but the three-dimensional analogs. So this is a very practical application of group theory. So group theory is very useful in science, not just in crystallography. It turns out to be very useful in physics as well. As a matter of fact, there's something called Noether's theorem. I don't talk about this in my book, but it turns out that there's various symmetries of the universe, like symmetry with respect to time translation, spatial translation, and rotation, and those give rise to the familiar conservation laws. Time translational symmetry is responsible for conservation of energy. Spatial invariance is responsible for conservation of linear momentum, and rotational invariance is responsible for conservation of angular momentum. So that's a very powerful result. So symmetry is very important in science, particularly in physics, but also in crystallography and I'm sure organic chemistry, anything involving molecules. Because molecules, not even even if it's not a crystal, molecules usually display various types of symmetry. For instance, benzene molecules are hexagonal, an H2O molecule, water molecule that has, I guess, bilateral symmetry. Looks kind of like Mickey Mouse's head, the two little hydrogen atoms as the ears, and then the oxygen atom is the main part of the face. I always thought it looked like Mickey Mouse. I don't know why. But anyway, enough of all that. So I guess that completes my talk for today on crystallographic groups. Thank you for watching. Long live math, and I'll see you guys next time. Bye.